Okay, so good evening, everyone. Let me see the screen. Okay, please anyone confirm if my screen is visible or not.
Yes, sir, it's visible.
Okay, yeah, fine. Okay, so today we are going to cover the week 5 content. So how many of you have gone through the week 5? Have you gone through the week 5 content?
So halfway through actually.
Okay, fine, fine. Okay. So week 5 content is all about tokenization. The content that we have seen till week 4, we assume that the data point that we feed into any of those models is a sequence of tokens, right? So this is what we were assuming till now, that the data that we are feeding is a sequence of tokens. So where are these tokens coming from? Or how do we build the how do we build the vocabulary, right? So the tokenization is the process. So this particular is tokenization that we are going to learn today. So is this is the process, or say these are the algorithms for building the vocabulary, right? Using a corpus. So how do we do that? That we are gonna see today. Okay. So one way you can think as like different words or the unique words in the corpus is your unique token. Or the token in the vocabulary, right? This is the one way of thinking of that. But it's not about just the one language. There are multiple languages, right? And different language has different morphological structures. They use different semantic needs, semantic words, and also we want algorithm which takes care of all those things, right? So it's not just uh, use the just the unique words in the corpus, right? So we are trying to create algorithms, or we are try to create algorithms which we can use in multiple languages as well, not just single language, right? So let's say you have a corpus you can think as a set of different documents, and they can have multiple language as well. But for now, just assume that you have a single language documents, or even they have multiple languages, right? So token can be based on characters as well. They could be words as well. They could be characters as well, right? So based on those processing unit for the tokens, we divide tokenization's algorithm into three parts. One is character level, another is word level, and third is subword level. So these are the three main uh, different algorithms in tokenizations based on the processing unit that we define for the tokens, right? So as the name suggests, if you look at the characters level, so what will be the characters level tokenizations? So in the character labels, each different characters is a token, right? So let's say you have an English sentence, or say any other languages. So English have the characters as A to Z, and alphabets. You have different symbols as well, or say the digits, right? So let's say you have A, B up to Z, and some numbers, or say digits 0 to 9, or some symbols as well, like different symbols. So all these becomes your tokens, different tokens. So in this case, what we are saying, the tokens are your characters, or say the bytes. If you or break it down on the bytes level. Okay, so those are called character level tokenizations. But is it a good tokenization? Is it a good vocabulary? If I use this as a vocabulary, or I say these are my tokens, and feed a sentence into a sequence of tokens, in this case, sequence of characters, will it be a good way to do that?
No, sir.
Why? So
Sir,
one way
because
is,
it will take, for
yes,
a
go
single
on.
sentence, it will take lots of spaces,
Correct.
Uh,
That is the one issue with the character level. A sentence will be a long, right? A sentence will be a long sequence of characters, right? Will be long sequence of characters, right? So in this case, it will take more space that you can think. Another thing is that the loss of information, right? Or let's say lots of semantics nature. Why? Because it's very simple. If I give you a sequence of characters, A to Z, some different characters I give you, and I ask you what is the meaning of those sequence, or what is the meaning, what are the meaning you are getting from the sequence, or what is the context you are getting from that sequence, you will be lost, right? Because those characters doesn't contains any meaning in itself, rather than the words, right? Words may have some meanings, so from there you can get some context. You try to get some semantic nature of that corpus, but the character table, it's hard to get the context, it's hard to get the semantic nature of the corpus, right? So we have the loss of information, loss of semantics, or lots of context if we use characters as the different tokens, right? So that's why model will fail to get the context even if we pass into the multiple heads that attention set, because right. So that is the some issues with the characters labels tokenization. That's why we generally don't use characters label tokenizers, right? Another thing you can think, another issues with the character level is that we have very small vocabulary, right? In this case, right, so you have only in if I talk about English only, so English had 26 alphabets, maybe some you add some symbols, digits, and all. Even after that, you will get very small vocabulary, right? So character labels tokenizers are not good tokenizers, right? So we generally don't use characters label. Next is that we have is word level tokenizers, right? So the second that we have is word label tokenizers. Again, the name is suggesting what it means. So let's say each different word becomes your a token, right? So let's say in the English, right? So you have a corpus. So there you will each or say each unique word is a token in the vocab, right? So okay, now here we have the context because word has some meanings and all, but it also has some of the issues. The one issue is that let's say you are training a algorithms or a tokenizers on a corpus, and that corpus may not contain some of the words, right? So those words are called out of vocabulary words, right? So these tokenizers, what it do, it gives the different tokens, right? Say unknown, right? So it provides some unique or the unknown token to out of vocabulary words, right? So in this case, what will happen that particular meaning of that word will be lost, right? Or so in that way, word level tokenization have meanings, but if the words is not in the vocabulary, right? It was not present during the training time, so those words are not handled well by these tokenizers, right? So this is one of the issues with the word level tokenization. And let's say you have some words which have spelling meaning in the test data set, not test data set, whenever you are doing inference using tokenizers. So in that case, you may have some words which has spelling errors, right? So those words will also be treated as a out of vocabulary words, right? So those misspelled word will also be not able to handle well by the word level tokenizers, misspelled word.
Sir, I have a
So
question.
yes.
Sir, in the unknown tokens,
Hmm?
will it like assign the same probability to all the unknown tokens, or is it also make a distribution of probability at the last
You're
for
talking
the
about the
unknown
models?
tokens? Yes, sir, for the unknown tokens which are
No, no. So every unknown tokens is treated as token UNK whenever you feed into a model, right? So it's not a
okay,
different tokens will get a different ID. It will get a unique ID.
okay, sir.
Okay, so that's why this is the issues with the word label. If the some unknown tokens comes or the misspelled token comes, in this case, it will the informations that word contains will be lost, right? So this is the issues with the word label tokenization. Other issues with the word label tokenization is that the vocab size that we get in the case of word label tokenization is very large, right? So we get very large vocab. Actually, we need very large vocab if we are using word label because we want most of the words in your vocabulary. Otherwise, your unknown words will be lost. And if we have large vocab, in this case, this embedding matrix, right, that we use in the models will be very sparse, right? So this is again one of the issues in case of word label tokenization, right? The another issues with the word label tokenization is that they are not language agnostic. Why? Why they are not language agnostic? Can you think of the languages where you will fail to divide into different words?
Japanese word.
Correct. Right. So language where we don't have delimiters, where we cannot divide into different words, right? But there are some multiple such languages where we don't have such marker where we can say that this is the different word or this is a different word. English is easy where we have a delimiter like white spaces or different markers like punctuation marks. There we can decide that this is my word. But again there are many languages where we don't have such way to decide which all words we have in the languages, right? Or even your if the language is very morphological rich, in this case also word label may have a kind of loss of information, right? So in that way, language these word label tokenizations, you probably need different tokenizers for a different languages, right? So that we want to create a tokenization we can use for different languages, right? So again, like it cannot be used for English and Japanese at the same time, right? So these are some of the issues with the word label tokenizers, right? So what we want, we cannot use characters label tokenizers, we cannot use word label tokenizers. Then what? We want something in between these two, right? Where we want our vocab size to be, what our goal? We want our vocab size to be moderate. It's in between somewhere character levels and word level, right? So we want it to moderate, and even we want to handle these out of vocabulary word or unknown words well. That we want algorithm where we can say that misspelled word or the rare words are handled by this tokenization. It's not that rare words are ignored or misspelled word are going to going into out of vocabulary world. So such kind of issues we don't want into the tokenizations, right? Tokenizer algorithms, right? So these things keeping in mind, we have some subvert level tokenizers, so that are generally used in the language models. So we have subvert level. So again, name suggests here the tokens are the subverts, right? So they can be birds as well, they can be characters as well, and they could be some subverts as well, right? So let's say you have player. So player is a word in English, so it can be play plus er, and those suburbs may have meaning. They may not have meaning as well. So it could be like we have PL as a one suburb, or Levi is a some suburbs, right? So those suburbs may or may not contain meanings, but you can think them as a substring from that particular string, right? Or the different words, right? So these are there are some words label tokenizers that we are going to learn in this particular week. Okay, so we are going to learn about three different algorithms for subvert. One is the first one is called byte pair encoders. Another is called a word piece, and the third one is called sentences. These three algorithms we are going to see how we use this algorithm to create the vocabulary. Okay, so we'll start with the byte pair encoders. So I'll explain the steps what algorithms do. Okay. So in the byte pair algorithms, so here what we do, let's say you have a corpus. Let's say you have a document, something like uh, let's say new as or set or let's say reset. Some these are some corpus birds. So these are the unique birds, and their count also we are taking from the corpus itself. Let's say new occurs 3 times, newest occur 2 times, set occurs 1 times, and this set occurs 4 times. Something. So what we have, this is my very tiny corpus. You can think as a different documents. Okay, different birds in the documents. Now these are my tokens or the birds in the tokens, and you have their frequencies as well. Okay. So what we first do, first we add a marker, right? Like bird ending marker. And why it is necessary, that will be also clear, the bird ending marker. So we add some marker here. In this case, let's say I'm adding W. Okay. So it is saying that my words has ended here. Newest my word now has ended. So actually, the purpose of adding the marker is that we don't want to create subwords which are where the characters are coming from two different words. We don't want like W and W we are coming from this word and N is coming from this word. We don't want such subwords in my vocabulary. That's why we add some markers so that tells that my words has ended there. Okay. So these markers are added in the first, I mean, pre-tokenization steps. Okay. Now what we do, first we take each bytes, right? So as the here name says, byte pair. So each bytes or say each characters. Now you can think as each characters. First we consider all the characters and their count. So it's easy part here. We take N, E, W, and that marker or say the placeholder. Then N, E, W, E, S, T. These all the unique characters becomes my the first vocabulary. Okay. Now so here we get S, T, S, E, T, we get R, E, S, E, T. So these all characters becomes my vocabulary. Okay. And here I'm keeping count as well because those count will be needed. So 3, 2, 1, 4. So the very first vocabulary that we create here is just the unique characters or unique bytes. Okay. If you think as different languages where characters are not well defined or like words are not well defined, you can think as each byte is your token. Okay. Here in this case, you have N, E, W, S, you have T, you have R, and EST all are used, right? Or marker, right? So this become my vocabulary. Now what I will do, I will now update my vocabulary, and there is a way to update my vocabulary. What I will do, I will look at each possible pair in my vocabulary. So like I will look at NE, EW, or all possible pairs, right? And I'll see in my corpus which occurs most of the most frequent, right? So pairs like NE, EW, NE. So pair, whenever I say pair, it means that N followed by E in my corpus, right? So how many times the pair NE occurs in my corpus? So what I'm doing, I'm looking at the
So 2 times.
5 times.
most occurring pair, most occurring pair I'm looking in my corpus. Which is the most occurring pair? You have to now. This is very exhaustive way to do that. I have to look at the all the possible pairs. So it's very tiny example here. So you can now tell me how many times N E occurs together in my corpus. The pair N E. So if I talk
Five
about
times.
the yeah, N E. So how many times? Look, 3 times here, right? 2 times here, and nowhere else it is occurring. So 5 times the count of n is 5. Similarly, let's say I am to count for EW, E and W. So how many times EW will occur? So 3 times here, 3 times here. Now this will not be counted, right? Because I'm looking for the pair EW. So the whenever I say pair, it means that E followed by W, not W followed by E. Okay. Otherwise, the pair will be merged. I mean, it will lose the meaning of pairing that, right? So here, so I will look at all such possible counts here of all the possible pairs, and I will look which pair is occurring most of the frequency of the pair is most. Okay, so in this case, assume that if you look at here, probably ES is the ST or S. I don't know. I have to count each or everything that will be very exhaustive task. So assume that ES, the pair ES is occurring. So here, if you look at ES is occurring 4 times, ES is occurring 2 times, 6 times here. So assume that this is the most. Okay. So what I will do in the next step, I will every occurrence of every instances of ES, I will replace it with the new token. Okay, so what I will do, I will add new tokens in my vocabulary, and that token will be ES. Okay, and every occurrence in my corpus is now here will become so every occurrence of ES, right? So what I will do, every uh, ES, I will replace it with ES. Okay, so in my corpus you have N E W. So here you don't have ES, right? You have N E W E S T. Right. So what I will do, I will replace this E as a different as a single token. Right. So I'll replace this as my single token ES and again W. And so here it will become SET, right? SET. So here again I need not to update. Here I need to update. What was that? Reset R. Yeah. So RESET, right? So this is how I updated my corpus, and the frequency will be remain same in the corpus, and your now vocabulary has become the initial characters was N E W S T R marker, and I've added one more token that is ES, right? So one more token has been added in my corpus. So this is called merge step. Okay, I'm adding I'm merging one token in my vocabulary. So this is called merge step. Again, I'll redo the same thing. Now I'll start so I will treat this as a single token now, right? So whenever I will pair ES with ES with where was ES again? Here, ES with T, W with ES. So let's say the pair becomes W and ES. So I will look at all the instances where W and ES are occurring together, right? So if now I'm to count how many times W and ES occur together, then what will be the count? WS occur. So here the count were 3, 2, 1, 4. So 3, 2, 1, 4. How many times W and ES are occurring together? So W and ES only 2 times, right? So the count of pair W and ES is 2 times. And let's say count of W and E. Can you tell me the count of W and E here in this now? Can you tell me the count
Zero.
W? Zero, right? Because here it is ES as a token, not WE as a separate token, right? So the count of W and ES becomes zero. W or E becomes zero, right? Initially it wasn't zero. So if you look at here, W comma E has some count. WE has 2 count here. So, but it has been updated now as per the different iterations. Okay. So you keep on doing this thing, and at each merge, at each merge, you replace all the instances, right? You replace of new token, right, in the corpus, and you add only one new token in the vocabulary, right? So this way you can keep on doing this thing until you get a desired vocab size. and you ended up with the new vocabulary, right? You probably do 20,000, 30,000 such merges. So you are keep on adding 20,000. I mean, at each step you are adding one token. So you will, let's say you started with the initial vocabulary size of 10, and you are doing 20,000 merge steps, right? Operations. So in this case, you will add 20,000 10 tokens in the vocabulary in the end, right? So this is how you build your vocabulary. Okay. And here you will see that rare was is also handled well, because let's say somewhere unknown words comes, right? Let's say in this particular I've done some in this particular corpus, I've done some let's say some k number of merge step, and I got the final vocabulary as, let's say, you have N, E, W, and all these things, and you have added EW, you have added NEW, you have added some ST, you have added EST. Okay, and so these becomes my final vocabulary, right? So now let's say new words comes. Let's say some word which vocab, I mean the corpus didn't which word wasn't in the vocabulary during the training time. So let's say some word, let's say rarest, let's say. Okay, so now if I want to tokenize this, how will do? So firstly, I will look at if the word present in the vocab or not. If it is not present, I will look at the merge operations. So like merge operation happen like initially it was these. The at the first merge EW was merged, and the second step the in NEW was merged. At the third step ST was merged, EST was merged, and something. So I will look at the sequence. So whether EW is present here is not, it's not present. I will look for the second merge NEW was present, here is not. ST is present, then I will do ST, and here I have rare as well, rare, right? And I will look at EST is present there. So EST is present here. So what I will do EST as my I mean, this will become my token. I mean, the split of this token. So I keep on doing this, and at the end, if I don't get, I will look at rare as is uh, tokenized as rare plus EST, right? So in that way, the unknown words is also got tokenized, right? So this is the way of doing byte pair encoding. Do you have any doubts in this? This algorithm is pretty easy. I mean, you do every time you look at the most occurring pair, and the most occurring pair is replaced in the corpus with a new token, and you add a new token in your vocabulary, right? So these steps you follow and keep on doing till your desired vocabulary is built. Okay, so any doubt in WP, not WP, this white pair encoding? Okay. Okay, so let's move to the next word tokenization, which is your word piece. Okay, so one issue with the BP is that these rare words are not, I mean, sometimes lose, doesn't got the right split or right tokens, right? So it doesn't handle the, because it's very greedy, right? Why it is greedy? Because at every step we are looking at the maximum occurring pair, right? So it need not to be true that maximum occurring pair may create a new subbird, which is actually is a meaningful subbird, right? Let's say in this case, I'm being greedy, and I got the bird as let's say WE as the most occurring pair, but in the end I don't get any subbird which using this pair which have some particular meaning, right? Or so it may happen that EST may lose at the end, because WE is already been created as a token, right? So it's being greedy at each step. right? That's why sometimes the rare birds got doesn't split in the rightful manner, right? So this is one of the issues with the byte pair encoders. Rare word doesn't handle well by this algorithm. So what we do, so this greedy natures BP is because of this deterministic way, right? Because we are looking at the highest occurring pair in the corpus and replacing them, right? So we want to add some probabilities to that. So we move to the next tokenization, which is bulk piece tokenization. So what we actually do, uh, what we here do, rather than looking at the frequencies, we define one scores, or scores you can think as a relative frequencies. Okay, let's say the word is the pair is EW, okay, or say ST. ST is the pair. I'm looking at the step, right? So what I will do for finding the score of pair ST, what I do, I find all the occurrence of where S and T are occurring together, and I divide it by the all the occurrence of S and all the occurrence of T from the corpus, right? This is the score I define. Okay, so if I define here, if I look at the same corpus, let's say you have corpus N E W, N E W E S T. Okay, I'm ignoring the end of marker that you can also add here. You have set, you have reset. The first step is same. I mean, you have created each characters as a different tokens, and the frequency is let's say 3214. Now, rather than looking at the highest count, what I'll do, I will look at the highest score here. Okay, so I will look at the score of E and W. So what will be the score? Score of an EW will be the count where EW occurring together, which is your three times here and two times here, which is five. I will divide it by the all the occurrence of E, right? So how many times E is occurring? How many times E is occurring? E in total in the corpus?
So 10 E's.
Yes, 10 times, right? So in each, not 10 times, actually two times more. Because three times here, two times here, two times here, right? So you have two more and two more here. So you have four more here. So you have 16 times,
So, sir, I
right?
want to ask something, sir. The in the newest sentence, the second one,
Hmm.
the word, if the character is repeating many times, so we have to multiply it with frequency. Like it is not taking its frequency. So 3 plus 2
No,
plus
no,
1.
no. I'm looking at the frequency of character E, right? So E is occurring here also. Now forget about the word. This is a word. Don't think it is as a word. You can think N as a different character, E as a different character or different token, and this E again as a different characters, right? So E actually is occurring two times in this particular word.
Yes,
So
sir.
in total, it will occur four times in this word itself,
Okay, sir.
right? Similarly, W is occurring 10 times total, and it is single time in each word, so it will be your 10 times. Eh? So this is the score that E and W got. So you find the scores every time, and you look at the final score. So what is adding new information to the byte pair encoding? The same algorithm is same. You can keep on doing things. You merge the highest scores tokens in your vocabulary and replace from the corpus, and the algorithm is same. Rather than just looking at the highest count, what we look here, we look at the highest score. Okay, in this case what happens, the this dividing makes it very good, because let's say you have a pair where the occurring together is 10 times, and the individuals count is very close to 10. Let's say only 10 times here, 12 times here. What does it mean? Here, this is, let's say you have bird, two bird, some bird, let's say alpha, beta, and here you have count of alpha and you have count of beta, right? Now, I'm saying that alpha is occurring in the entire corpus 10 times only, and beta occurring only 12 times, and both pair occurring together 10 times. What does it mean? Doesn't it mean that
Sir,
whenever
sir,
alpha, huh?
So they mean that they occur together more time rather than being separated
Yes,
because
yes. So it means that whenever alpha comes, it is most likely that it will come with the pair in the pairing with beta, right? Or say whenever beta comes, it is most likely that it will come in the pair with alpha, right? That's what it means. It's saying that alpha beta together is 10 times, and alpha again it again 10 times, right? So for alpha, it is very sure that alpha is followed by beta in all the occurrence in the corpus, right? Beta might have two instances where it is pairing with some other token, right? It is or it follows some other tokens rather than alpha, right? But we got some idea here, we got some intuition there. If the scores is very low, right? So in this case what will happen, score will be less, sorry, score will be high, score will be high. But if this individual counts is high, then in this case score will be less, right? So what we are doing, we are giving priority to the higher scores, right? The rare word, okay? Or the I mean, whenever they occur together, those scores become higher, and we are giving more priority to that high scores, right? So in this case it becomes better than the BPE, right? Entire algorithm is same, only thing is that the merging rule here, there we were counting at the most frequent pairs. Here, rather than most frequent pair, we are looking at the relative way, whether individually they are occurring more times or not, right? That also we are counting. So here this scores, defining scores makes BPs better. So this particular algorithm is called WPE, word piece algorithm, word piece tokenization. Any doubt in this? Okay, fine. One more thing, just want to tell you here that at the infer time, they both differ. Inference time, uh, let's say you have vocabulary that you have created. What we do in the BP, we keep on look. We can be at the each merge what we are adding, we store them, right? Let's say we have the initial vocabulary and we keep on adding. Let's say initial vocabulary is individual tokens, and you have added, let's say, ST here. The first merge, second merge, you have added ER, and you have added NEW somewhere, and you keep track of each merge token, right? So first step I added there here, and now let's say and now I'm to tokenize something. So let's say I am to tokenize player. Okay, so what it does, it actually first look if the entire word in the vocabulary is not. If it is there, the tokenization is the player itself, right? But let's say player is not in the vocabulary. What is that? It look at the merge steps, each merges, right? So first it will look whether ST is there or not. It's not there, fine. It looks for ER. ER is there, then ER it do like that. Then it keep on doing in the sequence, right? And let's say play is also there somewhere in the vocabulary. So it will tokenize that play and ER. Okay. So that's how BPE bus. But bird piece actually do different way, but most of the time they end up tokenizing the same way. Okay, but the base little different. You need not to track the sequence. How what is the actual sequence of merging? Let's say you have created the final vocabulary, and the final vocabulary. Let's say have the word play. It has ER. It has player, and it has let's say okay, some these words are there in the vocabulary. Now it doesn't require the sequence in which they are added to the vocabulary. It just look at the longest subsequence here. Let's say the player, let's say I'm to tokenize players. So it first look players is there or not. If it is not there, then look at the highest or the longest subsequence which is in the vocabulary. The longest subsequence, let's say the players is there, right? So it will do at the players and s, okay, something like that. So it look for the longest subsequence in the vocabulary. It doesn't count for the sequence in which they are merged in the vocabulary. So this is how they differ, but at the end, probably most of the cases, they end up doing the same tokenization, or the splitting of the word. Okay, so any doubt in these two algorithms? Okay, fine. One more thing, one more point that you can note here is that, let's say English has byte spaces as between the words, right? So there we know that the each what are the each words, and we can decide the marker, right? We can replace the or say we know the where the word is ending, right? But let's say the languages like Japanese or Chinese, right? So there each byte becomes your characters, right? And algorithm goes in the same way. In that way, you can say that it can be used for any language. It's not just English or any other language. You can use this algorithm for in most of the cases as well, most of the languages. Okay.
And so, what about punctuation marks like exclamatory mark
Punctuation
or
punctuation
apostrophe?
marks also, yeah, those marks also can be you at the time of normalization you can remove them, or you can even keep the symbols. Let's say exclamatory sign you want to keep into vocabulary. Let's say you don't want your some so these are taken care in the pre-tokenization steps, where you replace you firstly do lower casing, right? Because you don't want hello and hello to the different birds, right? So you want to treat them as a single token, right? So lower coding is done there. Somewhere like Unicode normalization is also there. Like somewhere you can see these birds is something like that. That is also taken care. Token you have different symbols, punctuation marks. That is also added into the vocabulary as well. But if you want to remove you that you can do. But normally it is added into the vocabulary as a new token.
So, sir, like the encodings we have done so far, like in character level also, if there is a punctuation mark, then we will count its frequency also.
Yeah, correct.
Okay, sir.
Okay, but how algorithm works? Like let's say you have full stop, right? So actually, you are full stop is generally in the English, it is followed by a white space, right? So what you do, you can ignore this part, and you can say that the NEW and my end of word marker is there. So right. So anyway, I'm looking for W comma and this count, right? W and end of sentence count, right? So there you need not to worry about this full stop. Let's say you have some any W and this marks exclamatory mark. So here you probably need this mark, right? So W followed by exclamatory marks and then followed by the white space, right? So some of those things you can ignore, like the full stops, because at the time of encoding you can replace your this W with the full stop or question mark based on this will be taken care of by decoding step, right? So you need not to add full stops and these in your vocabulary. Other symbols you can add, other punctuation marks you can add, but these common occurring, right? So this will this can be handled in the pre-tokenization steps.
Okay, sir. So, like they act like a delimiter, like comma, full stop, space.
Delimiters, yeah, correct.
Yes, sir.
Yeah, that those we can ignore because anyway we are adding like bird has ended, right? Okay, the next tokenizations is sentence pair, not sentence pair, sentence piece tokenizations. So what we do here, so you can think as again we start with building a suburb token vocabulary, suburb token. I mean the vocabulary which has suburbs as a tokens, and then we prune this vocabulary, right? So what is the first step here? So again it is language agnostic. The very first step is that every white spaces is replaced by the special marker, which is underscores. Let's say you have you have the corpus or sentence, which is your I like playing cricket, right? So in this case, what it does, every white spaces is replaced by this underscore. Okay, this is the very first step here. So in this way, you need not to worry about whether the sentence or the corpus or the language has white spaces or delimiter or not. Every language will be handled. If it has white spaces, it is replaced by the uh, this underscores. Okay, now what it does, it first find the initial vocabulary, right? So initial vocabulary, it uses generally some algorithm, let's say some created using extended suffix algorithm. So there is some algorithm which it uses to create the initial vocabulary. You can think is like finding some sub words. So you have a string here, right? A complete string as a corpus. You find some meaningful substring from that corpus. So or you just think it like finding different substrings of a different length. So of length 2, length 3, length 5. Some random you have started with. So you will get a very high size vocabulary, and it may have characters as well, let's say a b up to z, and some suburbs, some string as well, let's say it has ing, it has er, it has est, and different crick, and let's say et, all these substrings it has, and we have created very large vocabulary. Now our algorithm is to prune this vocabulary, and how we do that, that is we are gonna see now. Okay, now we have vocabulary with us, very large vocabulary. We have to prune this. For pruning this, first what we do, we use the EM algorithm. Okay, and for before that, what we look at the let's say you have a bird playing. Okay, so what are the possible split for this playing? From the vocabulary, initial vocabulary, we'll look at the any possible split. Let's say it has P, L, A, by I, N, G. It has play plus ing. It may be PL plus A by plus ing. So all the possible split for the playing. We look at which one is the which has highest score. Okay, and how we define the scores? The score is the log likelihood. Okay, so for finding these scores, what we do, we have the corpus, right? We have the corpus with us. We have the initial vocabulary with us. For every sequence, let's say X is your bird. In this case, playing is your bird. Now we look at all the possible split from the vocabulary. So let's say you have different split one, split two, split three, right? So out of these three, we look at highest score. And how do we find scores? So we look at the probabilities from the corpus. So in this case, the first split is PLA by ING. So I look at the count of I look at the count of L, I look at the count of A, I look at the count of all the birds, and the total tokens in the corpus. This becomes my log likelihood for the first split. Similarly, I look for the second split as well. Let's say I look at the play and ing. So what I'll do, I'll find all the occurrence of play in the corpus. I will do that count. Next, I'll do the count of ing. Uh, so count of ing, and then divided by the total tokens. So this will become likelihood for the second split. Similarly, I find the third split. Let's say third split was my PL A by ing. So I will look all the occurrence of PL A by ing and divide it by the total tokens. Okay, so these likelihoods becomes my scores now, and so and this scores will define which so out of these three, let's say you have three split, which one is the best split. So the one which is having the highest scores becomes the best split. So playing will be having best split as, let's say, third one or the second one. So play plus ing will be the best split for this playing. Okay, so I'm gonna keep this rule in mind, how to define the scores for a bird. This is how I define the scores for a bird. Okay, now the how to prune the vocabulary, that things and we need to discuss. Okay, so we have EM algorithm for that. Okay, so you have initial vocabulary, let's say some thousand size. Okay, now I am to reduce this size. Okay, so EM. So what is the E step for that? Yes, for each token in the vocabulary, I find the best split. Okay, for each token uh, in corpus, sorry, not vocabulary, corpus, find the best split. Okay, so I take an example. Taking example will be easy. So let's say you have a corpus with let's say you have lower. Okay, these two only. Let's take this occurring 5 times. This is occurring 2 times. Okay. Now my initial vocabulary. Let's say you have LOWER. You have LO. You have LOW. You have ER. You have WER. Here in this case, we have the larger vocabulary and prune this. Okay. So you have let's say OW. We have already not added. We have we also add the delimiter, that marker as well. So you can think as RE, W, and so very large vocabulary you has. Okay. Now what I will do in the first step, I will find the for each word in the token in each word in the corpus. So you have low, you have lower. Okay, I will find the scores. I will choose the best split. So low may have like L, O, W, and right, this split is there. There is like L, O, W is there, right? So there are different such split. I will choose the best split. Okay, which one will be the best split? I'll find the score using this log likelihood way, and I'll choose the best split for this particular law, right? And let's say it comes out to be, let's say comes out to be LOW. This comes out to be the best split. Similarly, I will look at the for the lower. Okay, let's say it comes out to be the low plus ER. Okay, so and I'll do this thing for each bird in the corpus. Now I corpus has only 2 birds. You can think as a very large corpus, and I do for each corpus and find the best split. Okay, so now my tokens become these things, and the in the next step, what I'll do in the M step, I'll find the I'll recalculate the probabilities, right? So what I'll do here in the step, discard those tokens which has the least. I got some tokens here. Like let's say I got low here, one token. I got low here, ER here. Okay, so these tokens has very least probabilities, right, in occurring into the token. So these I prune them or I exclude from the vocabulary. Exclude the least occurring token. Okay, and then in the M step, I again recalculate the probabilities for each word. Again, I will look for the low and lower. And at one stage, there will be a way where this probability will not change. So right. So here, let's say the low for low is this probability is coming out this one, right? So the low the count of low account total things. But at one stage, there will be a time where these each step probabilities are not changing. In this case, you will have a final vocabulary. Okay. So this is how you find the vocabulary for the sentence piece algorithm. Okay. So again, what we do, we start with a very large vocabulary. This is created using some algorithms. You can even think as a BPE. You created this using BPE. Okay. Now what I'll do, I'll start pruning this. And for pruning this, what I'll do for each word in the corpus, I find the log likelihood score and choose the best split. Okay, for low, this is the best split. For lower, this is the best split. And according to those split, I'm only interested into those tokens, and I'm excluding those tokens which are not adding much information to my birds. Okay, because those tokens are not giving me the best split, right? Best split, I'm keeping only those tokens which is giving me the best split. Okay, so the tokens which are least used or least probability has least probability scores, I'm discarding those tokens, and then again calculating
So,
the probabilities at the M steps. Yes.
sir, is there any threshold to choose the to exclude the least occurring tokens? How many we have to exclude? Is there
Yeah,
any
so
threshold?
at least, so it depends upon your initial vocabulary size and the final vocabulary size that you want to build. Let's say you have 10,000 initial tokens and you want 10 only, let's say 1,000 tokens in your vocabulary. What you do, you start excluding 5% of the tokens or 10% of the token at each token at each step, so that you can predefine how many tokens I want to exclude at a particular step.
Okay, sir. Thank you, sir.
Okay, so this is one thing. Now, if I go back here, the E step where I'm saying that this low, I will find the best split. So look at this step more closely. So let's say low, right, and or say lower. I want to look at the best split. Okay, now I have the vocabulary with me, right? So I will look at all the possible split here. So all the possible will be L plus O plus W plus E plus R, something like that. This is my one split. Let's say second split is my LO or WE and R. Third split is LOWER. And let's say there will be a multiple such split in the bay, right? So do I need to look at all the possible split? So I will find the scores here, n of s1, n of s2, score here, and I will choose the best one. Let's say the best one comes out to be this one, and I say that this is the possible split at the e step, and I'm more interested into these tokens rather than lo. And one more thing, always keep characters. Don't exclude them. You need not to exclude the characters, right? Apart from some words, you generally exclude them, right? So L, O, W, E, and let's say R, this thing. I am not much interested into these tokens because these, in this case, it's very low, low corpus, but you may think of very high corpus, and there may be some tokens which are not even adding higher value to my corpus, right? So rather than looking at all the possible candidates, so here I have three candidates, but in larger birds, or say even in the case of lower, you may have multiple base. So that's two raised to power five, right? One, two, three, four, five. Five such candidates you have, right? If I say each word or each L O O W W E E R, all such becomes my different suburbs. In this case, you may have such two raised to power five such candidates. Do I need to look at all the such possible pairs to find the scores or to find the best split? No. So for that also it uses different algorithm, which is called bitter V algorithm, right? So this is for finding the best candidates, right? Finding candidates for best split. It's not associated with the tokenization. It's just used for finding the best candidates for splitting, right? Which one to choose rather than looking for each candidates, which candidate to look. Okay, so how this work? So let's say this is a dynamic programming algorithm. So we are not going into that details. So in this case, how it works, that's I'm just explaining. So let's say you have a bird player. So what it do, it start with the uh, from the first character. So it start with the play PL. Okay. So what are the possible way of splitting PL? One is like P and L, and another is just PL is as a bunt token, right? So now it is look at the scores of PL and PL as a single token. And let's say scores comes out to be here minus 0.5. Here it comes out to be minus 0.4. So the larger one is this thing. If keep these things and discarded this from the all the possibilities for this PL, right? So again, if because we have discarded PL as a token, as a separate token, it doesn't exclude all the candidates where P comes out to be a single token, right? So let's say one of the possible split was PLA by ER, right? This might be one of the possible split, but I've already discarded this thing that P won't be occur as a separate token, because here I'm saying that I'm choosing whenever PL comes, I'm choosing PL rather than PNL, right? So in that way, it discards all those possibilities. Then again, it look for the next word. It looks for the A as now. Now, what are the possible way of PL and A? It is PLA or PLA as a single token. Now it again look at the scores. Let's say here it is come out to be minus 0.3 here, minus 0.4 here. Again, it will keep this thing rather than keeping this thing. So all the possibilities where PL was coming as a separate tokens, and other comes and it has already discarded this. It will only look for where PLA is, where it is starting with at least PLA, right? Again, it will go for PLA and look for the next word, which is by. Now it will look for whether how it can be splitted. It can be splitted as PLA and by as different tokens and PL by as same tokens, right? So again, it's looking for these scores. Let's say now it comes out to be 0.1 here and 0.3 here, right? So in this case, now it will discard this thing and keep this thing. Okay, and it keep doing this way and discarding the candidates. Okay, so this is how is used in this particular sentence piece algorithm. Apart from this, even if you avoid this algorithm, the computations will be large. You have to look at each candidates to find the best split, and you have to do E and M steps iteratively. Okay, until you get the final vocabulary. Okay, so this is how your sentence piece work. Any doubt in sentence piece? So any doubt in sentence piece algorithms? Okay, so I hope this is clear. If not, we can discuss it later as well. No issues. Uh, and go through the content, the lecture slides. Uh, these three algorithms are covered in week 5. Apart from that, the just the introduction, what is tokenization is and what are different ways of tokenizations. Okay, so this is your tokenizations. Now you know how to get the token, how to create the vocabulary, and the next step you already know about models and all. Okay, so this is all about week 5. If you have any doubts, you can ask. Otherwise, we can close it now.
Thank you, sir.